Hello, my project topic is Amazon delivery time prediction. This is a supervised machine learning regression project. The project summary is this project leverages machine learning to predict Amazon delivery time using detailed e-commerce agent, product, environmental, and route data through systematic steps, data preparation, cleaning, feature engineering, exploratory data analysis, multiple regression modeling, and experiment tracking. The solution can forecast delivery completion time based on other parameter and real-time condition. With the ability to ingest new order details and generate accurate prediction, this model will support logistics team by enabling smarter scheduling, reducing operational cost, and improving customer satisfaction. This includes Streamlit front-end enabling, which help users to input variables and instantly receive estimated delivery time. Ultimately, the project's outcome help Amazon optimize delivery performance, streamline supply chain operation, and deliver a superior customer experience. This is my GitHub link for the project. The problem statement is this project leverages machine learning to predict Amazon delivery time using detailed e-commerce and with the ability to ingest the accurate prediction of the delivery time. Now let's begin the analysis part. These are the required libraries which I have used in the project. This is the first four column of the rows of the data set, which includes the order ID, agent age, agent rating, store latitude and longitude, and so on. There are 43,739 rows and 16 columns in this data set. These are the data type of the columns. Like order ID is object, which means it is an unique value. Agent age is integer, agent rating is float, store latitude and longitude you can see it's float, which is wrong. We have to correct this. And order date and time is also here is also keep as object, which we will change in the next part. Now I have checked if there is any duplicate value in the project or not. So I can see there are zero duplicate values, and I have checked the missing values in the data set. This data set doesn't contain any duplicate value, but there is some missing value for agent rating and weather conditions. What are the columns of the data set? Order ID, agent age, agent rating, store latitude, store longitude, store drop latitude, drop longitude, order date, order time, pickup time, weather, traffic, vehicle, area, delivery time, and the category of the product. This is the statistical summary of the data: the count, mean, SD, minimum, maximum, and the median and quartiles. Variable description, order ID, unique identifier of each order, agent rate, age of the rating of the delivery agent, agent age of the delivery agent, store latitude, longitude, graphical represent location of the store, drop latitude, longitude, graphical location of the delivery address, order date, time and date of the or when the order was placed, pickup time when the agent pick up the order, weather condition during the delivery, traffic condition during the delivery, vehicle mode of transport used for delivery, area, type of delivery area, delivery time, target variable representing the actual time for delivery in hours, category of the product. Both order ID and product category were removed to eliminate irrelevant or non-informative columns. Order ID is just a unique identifier and does not help in prediction, while product category was not relevant to modeling delivery time. This streamlines the data set, focusing on Useful features. Now we come to univariate analysis. This is a graph. This is a histogram, and it shows the distribution of delivery time with respect to the count of the orders. This histogram was chosen because it shows the delivery and frequency of delivery time, making it easy to spot typical values and outliers. Most delivery fall between 100 and 150 minutes, but the presence of long delay is notable and indicates some influences. This insight can lead to business improvement by focusing action on reducing late deliveries. However, if long delivery time persists, they can harm customer satisfaction and potentially lead to negative business growth. This is a graph of delivery time with respect to weathers. The box plot was chosen because it easily compared delivery time across different weather conditions, highlighting medians and outliers for each category. Deliveries can take less time in sunny weathers and slower during cloudy and foggy conditions, suggesting weather impact efficiency. This insight help by showing where delays are likely, supporting better resources planning. Negative impact can occur mainly during fog and cloudy weather, leading to slower deliveries. This is a violin chart showing the distribution of traffic with respect to the delivery time. Deliveries in lower traffic area are generally faster and less, while those in high traffic or jam have longer and more spread out delivery times. These insights support business improvement by highlighting the need to plan around peak traffic period. Persistently long deliveries in high traffic condition can negatively impact customer satisfaction. This graph shows the correlation scatter plot between agent rating and delivery time. It can help to identify any correlation between the agent rating and the delivery time. There is no clear relationship between higher agent rating and faster delivery times. This insight can improve can this is insight suggests that improving agent rating alone may not sufficiently reduce delivery times, prompting focus on other operational factors for business impact. Next, this is a box plot for vehicle type with respect to delivery time and delivery area with respect to delivery time. Motorcycles deliveries show higher average and more variable delivery time compared to scooters, vans, and bicycle. Bicycle generally yield faster and more consistent deliveries. Semi-urban area have significantly longer delivery time while little variation, while metropolitan area have moderately longer time, and urban and other area have comparatively shorter delivery duration. This finding can guide us as vehicle choice for optimal efficiency, helping the business reduce delay. Relying heavily on solar vehicle like motorcycle for average delivery could negatively impact growth if not managed. These insights can drive focus operational improvement, especially for semi-urban and metropolitan zone, enhancing efficiency and customer satisfaction. Longer delivery time in a specific area may negatively impact growth if not addressed, as delayed delivery reduce customer loyalty and increase cost. This is a correlation heat map. Here we can see that agent age has a positive correlation with delivery time, while agent rating is negatively related. Other features show little or no correlation.
In progress.
Improving agent rating may reduce delivery time while no negative growth is directly suggested by the weak correlation of other feature. Mm. Next, we proceed to feature engineering and data preprocessing. We have seen that there are missing values earlier, so we have counter it and recheck that if there is any missing value present there or not. Mean what missing value technique I have used? Mean imputation for agent rating. Missing values are replaced with the mean of existing rating. This method is used because agent rating is a continuous numerical value and mean imputation preserves the overall average of the data, minimizing bias. Mode imputation for weather and traffic. Missing values are replaced with the most frequent category mode. Mode imputation is suitable here because weather and traffic are categorical variable. Using the mode maintain the most common and avoid introducing invalid values. These techniques were used to retain as much as possible without dropping rows, while missing values with statistically representative substitute to minimize distortion and improve model sustainability. The outlier treatment which was used was value replacement. Specifically, the agent rating values of 6, which is outside the valid range, was replaced with the agent rating, mean agent rating. This technique was chosen because it correct an obvious data entry or validation error without losing data. It preserved the original data distribution and size since only the incorrect values change. It avoid over aggressive outlier removal or capping that may distort true variability, especially since other outliers were considered genuine reflections of the data. Overall, this approach keep data integrity while resolving clear error, aiding stable and realistic modeling. Next, I have converted the date columns to date and time columns. This code perform date and time conversion and feature extraction of the order and pickup date and time. Convert the date order column to date time format to ensure consistent correct date time representation. Cohesion handle invalid dates gracefully. Extract the date of the day of the number of week, for example 0 to 6 from order date, creating in order day of week. This is useful as a categorical feature for model or analysis. Converts order time and pickup time column to date time object with only time precision, coercing errors to NAT for invalid times. Extract the hour from order time and pickup time, storing them in order hour and pickup hour. Hours are numeric features representing the time of the day correspond to order and pickup. These transformation are enabled the use of data and time information as actionable features in analysis modeling, preserving the temporal pattern that may have impact delivery times and other outcomes. Next, I have filled the missing order values with the median to avoid gaps and data and keep data consistent for analysis and modeling. Calculating the actual distance from store location to drop location. And this is helpful because it provides a meaningful measure of delivery distance, which is a key factor affecting the delivery time and operational logistic. Instead of using raw coordinates, this matrix captured the Earth's surface distance between the 2 points, improving modeling and analysis for delivery efficiency, route optimization, and performance prediction. Next, categorical encoding. This method converts each categorical variable into multiple binary. One per unique value indicates presence 1 or absence with 0 of that category. Machine learning model require numerical input, so categorical value must be converted. One hot coding avoid imparting any unintentional ordinal relationship among categories. It is straightforward and effective for normal categories. Normal categorical features like weather, traffic, vehicle, and area. Using D-type int ensure the coded columns are 0 or 1 values ready for modeling. This approach preserves all category information while making the dataset compatible with many machine learning algorithms. Columns such as store latitude, longitude, drop latitude, longitude, traffic NAN, order time, pickup time, and order date. These columns are dropped to remove redundant or less useful information. These coordinates were replaced by calculating distance, and raw datetime were replaced by extracted time features. The traffic NAN column was dropped after imputation. Dropping them simplifies the dataset and improves model performance by keeping only relevant features. Now the transformed data set look like this, which have day of the week, delivery order hour, pickup hour, and the distance calculated is also there. Feature selections. The primary method used here is manual feature selection, where delivery time is target is separated and all the other column are used as input feature. These indicate prior processing in identifier relevant features for prediction and drop or transform others. Features like calculated delivery distance, order pickup hour, categorical dummies is are and categorical dummy data are written. These features are important because they capture key factors such as time of the day, route length, coordination, and transport mode that affect delivery speed and efficiency. Data scaling was not performed because models like gradient boost and random forest are tree-based and do not require feature scaling to perform well since they split data based on threshold, which are independent of feature or magnitude. Linear regression benefit for scaling, but if non-tree models are less emphasized, scaling is key for simplicity. Geospatial data coordinates scaling does not require improved performance as the raw coordinates or derived distance hold physical meaning. Splitting of the dataset. This dataset is split into two different parts, 80% training and 20% testing. This is a common practice because it provides enough data for the model to learn effectively while reserving a representative proportion to evaluate its transformation performance or on unseen data. The random state 42 ensure reproducibility by consistently producing the same split across runs. Now moving on to the model and ML modeling. This is the ML flow in which I have used linear regression, random forest, and gradient boost simultaneously in the same code with the help of the function loop. And we can see that and the evaluation metrics considered here are RMSE, root mean squared error, MAE, mean absolute error, and R square. The final prediction model chosen is the gradient boost because it achieved the best performance metrics among the three. The gradient boosting model has the lowest RMSE and MAE, indicating the most accurate and consistent prediction, and the highest R square showing the best fit to the data, reflecting its ability to accurately predict delivery time in varied conditions compared to linear regression and random forest. Next, we save the best model by deployment. The best performing machine learning model was serialized and saved using job for efficient reuse and deployment. The file name was dynamically generated based on the model name, enabling better model management and version control. This approach ensures the model can be loaded later without retaining, saving computational resources and enabling smooth production. Conclusion: this delivery time prediction project successfully developed and evaluated multiple machine learning model using key performance metrics aligned with business goal. The gradient boosting model was selected for its accuracy and ability to capture complex underlying pattern, reflecting by the lowest RMSE, MAE, and the highest R square score. Feature engineering includes geodesic distance calculation and encoding category variable played a significant role in improving model performance. The project demonstrated the importance of iterative model, rigorous evaluation, and data-driven feature design for building effective predictive solution. Future work could include applying model interpretability technique to further understand feature impact and support transparent decision making. Thank you.